Hello all, myself Siraj Sonasra from Faculty of Technology, RK University. In this GATE mechanical video lectures, I am going to explain engineering thermodynamics. Here in the first part, I am talking about engineering thermodynamics, laws, relations. This is the theory part, and then after 2009 to 2019 GATE example solution. So approximately here 10 years GATE example we solved. So let's start with the gas law. So first we start with the gas law. So first gas law is the Boyle's. So Boyle's says that at constant temperature, the volume of the gas is inversely proportional to pressure. It means that if the volume is increased, pressure is decreases. It's or vice versa. So volume increase, pressure is decreases. So if we write here V upon P is equals to constant, if we rearrange this term, then we can write in this manner. That's why we can write this term V1 by P1 is equals to V2 by P2 is equals to constant, or we can rearrange V1 by V2 is equals to P1 by P2. So this is the relations of volume and pressure if the temperature is constant in the Boyle's law. Now second law is a Charles law. So Charles stated that volume is directly proportional to temperature at constant pressure. So if you put the pressure is constant and volume is increased, then temperature of the gas is also increased, or temperature increase, the volume is increased. So vice versa we can say. So if you write this terminology in that way, V upon T is equals to constant. If you put this T in denominator of the V, then we can write this terminology V upon T is equals to C. If we elaborate it, then V1 upon T1 is equals to V2 upon T2 is equals to constant. That's why we can write over here V1 by V2 is equals to T1 by T2. So this is the relation of volume and temperature at constant pressure in Charles law. Third one is a Gale-Lussac's law. So Gale-Lussac says that pressure is directly proportional to temperature at constant volume. So if we increase the pressure, the temperature of the gas is also increased when the volume is constant. So if we rewrite this terminology, then we can write P upon T is equals to C. That's why we can write P1 by T1 is equals to P2 by T2. If we rearrange this term, then P1 by P2 is equals to T1 by T2. So we can get the relation between the pressure and temperature at constant volume by the Gale-Lussac's law. So here we have a three relation between pressure, volume and temperature, which we can easily remember for a solution of example. Now let's move. The second thing is equation of gas, or gas characteristic equation, or the characteristic equation of the gas. So we already know the gas characteristic equation is equals to PV is equals to mRT. This is the gas characteristic equation. So how it will come? Let's start. So if we combine the Boyle's and Charles law, So we know the Boyle's law. Boyle's law is V is inversely proportional to P, or volume is inversely proportional to pressure. And Charles' law, it is V is proportional to T. So if you combine these two laws, then you can write V is proportional to T upon P. If you remove, this is the relation, or we can say this is a combination of Charles and Gay-Lussac's law, Charles and Boyle's law. So if you rewrite this terminology, then we can write, or we can say, if we remove this proportionality constant, then we can write P into V. P we can write on besides the V, P into V, and if we remove this proportionality, we put some constant R and temperature T. So we can write over here P is equals to RT, or P into small v is equals to RT. So this is for 1 kg of gas. If we consider m mass of the gas, then we can write P into capital V. This is the total volume. Here it is a specific volume, 1 kg volume, is equals to m into R into T. And this equation is called gas characteristic equation of the gas. And here the R is a gas constant, or characteristic gas constant, and here the unit of the R is kilojoule per kg into Kelvin. So if we rearrange this terminology, R is equals to PV upon MT, and if you put the unit of each and every property, then we get this unit of the R. So this is very simple, gas characteristic equation, PV is equals to MRT. Then after, the universal gas constant, RU, it's denoted with the RU. RU is a product of R, which is a gas constant, and molar mass, or molecular weight. So here the product of gas constant and molar weight, it is called universal gas constant, RU, and its value is fixed, or we can say the same for the all gases, and its value is 8.314 kilojoule per kilogram into mole into Kelvin. So if they are asked the value of R is 8.314 kilojoule per kg into mole into Kelvin, so this unit and the values you need to remember, because maybe used in different example. So RU is 8.314, and this value is same for the all gases, that's why it is called universal. Here it is a local, R is a local, because the value of R is vary with respect to gas, different gas. If you take the oxygen, the value of R is different. If you take the carbon dioxide's value is different. But if you take RU, it means that the value of R is constant, or we can say same for all type of the gases. Now here is the Avogadro's law. So what Avogadro says? Avogadro says for equal volume of different gas. So if you have two gas, equal volume means one gas is A and second gas is B, having the same volume. So I write over here is equals to volume is same, so VA is equals to VB. This is my gas B. If the equal volume of different gas both are different, A and B, at the same temperature and pressure, so I can write over here the temperature of the both gases, TA is equals to TB, and pressure PA is equals to PB. TA is equals to TB and PA is equals to PB. If this condition is arrived, then we can say the both gases are contain equal number of molecules. It means that Na and Nb, number of molecules in A gas, is equals to number of molecules in B gas, and this is called Avogadro's law. So it's simply defined that if you have a oxygen, okay, and if you have a carbon dioxide, the two different gas, but its volume, temperature and pressure are same, then if you count the number of molecules in given volume of oxygen and carbon dioxide, you found that both have a same number of or equal number of molecules. So this is the relations of we can say molecules by the Avogadro's law. So next, here the classification of the gas. So gas classification. So gas classification. How we classified the gas. So gas mainly classified into three categories. First one is a perfect gas. Perfect gas. So what is the perfect gas? So perfect gas, we consider the perfect gas those gases which obey or follow PV is equals to MRT relation. Means here they need to follow this relation. Here the volume on the left hand side and right hand side both values are same, then we can say for the particular gas they obey this relation. So the gases which obey the PV is equals to MRT equation and volume and specific at constant pressure and specific at constant volume. The value of these two is constant. It does not change with respect to time, or we can say temperature and pressure, any other properties. So these two relations are established when PV is equals to MRT and Cp and Cv values are constant, then this gas are considered as a perfect gas. Okay. Second one is a quasi-perfect gas. Quasi-perfect gas. So quasi-perfect gas is quasi-perfect gas. Quasi-perfect gas obey PV is equals to MRT relation, but Cp and Cv does not constant. These values are vary. These values are not constant. They are already obey this PV is equals to MRT relation, but value of Cp and Cv are not constant. This type of gases are categorized as a quasi-perfect gases. And third one is a real gases. Real gas. So here the gases which does not obey or follow PV is equals to MRT. So all the gases which are available in the atmosphere are real gases, because we know there does not follow the PV is equals to MRT relation. So we can say oxygen, carbon dioxide, nitrogen, these all are real gases. They are not a perfect gas. So simply we says that the perfect gas does not exist in the atmosphere. Quasi-perfect is also not exist. These two gases are just sake of learning. They are not exist in the real life. But all the gases we are considering are real gases. What we are observe in the atmosphere, they all are real gases. So this is the very basic thing which we need to understand, the difference between the different gases. But when we are derive something theoretically, at that time we are taking the all gases are perfect or quasi-perfect, because at that time if we say it's not obey the PV is equals to MRT relation, gas characteristic equation, then the relation which we are established, or we can say the experiment which we are carried out on the gas, that become very lengthy and complex. So we are considering the perfect gas. Those gases we are considering a perfect gas. So now here the two terminology, Cp and Cv. So let's see about the Cp and Cv. This is called a specific heat. So specific heat. So what is a specific heat? Specific heat is a energy storage capacity. It is also called energy storage capacity, or you can say thermal capacity. Thermal capacity. So what is the thermal capacity or energy storage capacity? Is the amount of heat required, amount of heat required to increase temperature by 1 degree for 1 kilogram substance. So its simple meaning is that here, if you have a 1 kilogram of oxygen and if you want to increase the temperature by 1 degree, then the amount of energy required or heat required to increase this temperature, it is called specific heat, or we can say thermal capacity or energy storing capacity. So this is the basic definition of the specific heat. Now specific heat have two types. One is a specific heat at constant volume, and second one have a specific heat at constant pressure. So first, CV, specific heat at constant volume. It is the definition of the CV is nothing but it is a amount of energy required to increase the temperature of 1 degree for 1 kilogram substance when the temperature of the gas is constant. So, and we can elaborate it, or we can write these things du upon dt, and that's why if we rearrange this term, then du is a CV into dt. Okay, and here the du is equals to CV into dt for 1 kg of gas, or 1 kg of gas. But if we write this equation for m mass, then we can write du is equals to m CV into dt. So this is a very important equation for us to derive the different relations in different condition. We can say PVT relations, in work relation, in internal energy relation. So remember this equation. This is a very important equation. Second thing is CP, and CP is definition of the specific heat at constant pressure is amount of heat required to increase the temperature of 1 kg of gas. Sorry, increase the temperature by 1 degree for 1 kg of gas at constant pressure, and we can write this CP is dH upon dt, where dH is a change in enthalpy. So that's why we can write over here dH is equals to CP into dt. This equation is for 1 kg of gas. So if you write this equation for m mass, then dH is equals to m CP into dt. So this is a very important equation also to establish the relations for the different condition. So here the mean two equation is du is equals to mcv dt and dH is equals to mcp dt, and these two equations you need to remember. So here the part of the gas classification and specific heat are over. So let's move with the relation. So here we are established the relationship or relation between CP and CV, because this relation maybe we use in the example. So we know first one is adiabatic index. So what is the adiabatic index? So adiabatic index, it is the ratio of, it's denoted with the gamma, and it is the ratio of specific heat at constant pressure upon specific heat at constant volume. CP by CV, it denotes with the gamma, and it is called adiabatic index. And for gases, or we can say for air, we are taking the value of gamma is 1.4. So for different gases, we are taking the value of gamma is 1.4. This is a common value for the air, but the values differ for different gases. So now we know the enthalpy is equals to U plus PV. This relation we already established, as H is equals to enthalpy, U is equals to internal energy, P is a pressure, and V is a volume. So enthalpy is a summation of internal energy and flow work. These two terminology combined product of the pressure and volume, it is called flow work. So that's why here we can write U plus, here we know the gas characteristic equation, PV is equals to mRT. So we can write over here, instead of PV we can write here H is equals to U plus RT. Okay, so here we establish one relation, H is equals to U plus RT. Now if we differentiate this equation, then we can write dH is equals to du plus R is constant, R into dt. That's why if we divide this whole equation by dt, then dH upon dt is equals to du upon dt plus R. If you divide the whole equation by dt, here dt, and here dt, then this equation comes in that way. But here we know dH upon dt in previous slide is called specific heated constant pressure. Cp is equals to du upon dt, it is called specific heated constant volume, Cv plus R. So simply we write R is equals to Cp minus Cv. So this is the first relation between the R, Cp and Cv. Now the second one, here I write over here, draw line. So let's start. R is equals to Cp minus Cv. So if I divide the whole term with the Cv, so in this equation can write Cr upon Cv is equals to Cp upon Cv minus 1. If I divide this whole equation by Cv, so R upon Cv, Cp by Cv, and Cv cancel out, so 1. So here R upon Cv is equals to, we know Cp by Cv is a gamma, it is a adiabatic index, so it is gamma minus 1. So if we rearrange this term, then Cv is equals to, put the Cv over here, multiply over here, then we can write Cv is equals to R upon gamma minus 1. So this is the relation between Cv, R and gamma. Next, R is equals to Cp minus Cv. Divide this equation with Cp. So R upon Cp minus Cp cancel out, is equals to Cp cancel out. So 1 minus Cv by Cp. So if we write this equation, 1 minus 1 upon Cp by Cv, right, in denominator to denominator. So here the relation is R upon Cp is equals to 1 minus 1 upon gamma, because Cp by Cv is a adiabatic index. This one, Cp by Cv is adiabatic index. So here we rearrange the term. So take the LCM, so gamma minus 1 upon gamma. So finally Cp is equals to, multiply this Cp over here, R into gamma upon gamma minus 1. So this is the second relation between the Cp, R and gamma. So in the whole slide we have a relation between the Cp, Cv, R and gamma. So it is very important for us. First relation is gamma is equals to Cp by Cv. Second relation, R is equals to Cp minus Cv. Third relation, Cv is equals to R upon gamma minus 1, and fourth relation Cp is equals to R into gamma upon gamma minus 1. And this 4 equation is very important for us as exam point of view, because in the example, if the value of the Cp and Cv is given and you want R, then at that time you can calculate the R by this equation. So maybe ask in the examination directly or indirectly. So remember this relation. Now the next. So here the most of thermodynamics basics is completed. Now let's start with the thermodynamics processes. So here thermodynamic processes, thermodynamics process. So we know we have so many thermodynamic processes. So let's start with the basic processes. Isochoric process. In isochoric process, volume is constant. This process, the process in which the volume is constant, then it is called isochoric process. Second one is a isobaric process. So isobaric process in which the pressure is constant. And third one is a isothermal process. In which temperature is constant. Here fourth one is a adiabatic process. In which the heat transfer is 0. Then after isotropic process or isentropic process in which enthalpy H value is a constant. Sorry here not enthalpy, but here it is a entropy is a constant. Isentropic, so S is a constant. Sixth one is a isenthalpic process. In isenthalpic process, H value of enthalpy is a constant. And then after polytropic process. So such a different process are carried out in the thermodynamics as per the requirement. So here in this session we have tried to establish the relation of PVT, pressure, volume and temperature. Second is a work done. Third one is heat transfer, and fourth one is internal energy for all four processes. So, and it is very important for calculation of the example. So we have tried to establish the relation of PVT, work done, heat transfer and internal energy for the isochoric, isobaric, isothermal and adiabatic process. And it's very important because whatever the relation we are get from this process, it's very useful to calculate the example. So keep in mind these things. So let's start with the first process, isochoric process. So first process, which is isochoric process, and we know isochoric process is the process in which the volume is constant. So here the volume is constant. So first relationship is PVT relation, PVT, pressure and volume and temperature relation. So how the PVT relation is established in isochoric process. So we know gas characteristic equation PV is equals to mRT. So if we rearrange this term, then we can write PV upon T is equals to M into R, where M is a constant and R is also constant. So we can write over here PV upon T is equals to constant. So here if we write this term PV upon T is equals to constant, that's why I can write for different point P1 upon V1 upon T1 is equals to P2 upon V2, sorry, P2 into V2 upon T2 is equals to P3 V3 upon T3 is equals to P4 V4 upon T4, so on. So PV upon T is equals to constant. So we can write this relation in that way, but here we know in isochoric process the volume is constant. So if the volume is constant, so it means that we can write at any point V1 point or V2 point or V3 point or any point V, the value is same, constant, the values does not change. So V1 is equals to V2, so we can remove this, V1 is equals to V2 equals to V, so we can write P1 by T1 is equals to P2 by T2 is equals to P by T. So that's why we can write over here P1 by P2 is equals to T1 by T2. So this is the relation of pressure and temperature in isochoric process. This is our first relation. Now second one is a work done. How much work is done in isochoric process? This is the PVT relation. So in work done, the equation is W is equals to 1 to 2 integration P dV. We already know this thing, pressure into change in volume. But here we already know, we can write this equation in that term 1 to 2 P dV is a change in volume. So we can write V2 minus V1. But here in isochoric process, the volume is constant. So V1 is equals to V2. So if we write this relation 1 to 2 P V2 minus V1 is also, we can write V2. So V2 minus V2 is 0. So here this total values become 0. So definitely we says that in isochoric process the work done is equals to 0, and this is very important. For the isochoric process, if the volume is constant, then you does not get any kind of work as an output, or work done is 0. Now third one is a heat transfer. Heat transfer. So we know the first law of thermodynamics. As per the first law of thermodynamics, dq is equals to du plus dw. Q is equals to u plus w. This is the in differential form. So dq is equals to du plus dw. But here, if the total volume is 0, then we can say change in volume is also become 0. So dw is also 0. So here the work done is 0 in isochoric process. So you can write over here dq is equals to du. But in the previous slide we already discussed this thing. Du is nothing but it is a CV dt. We already know this terminology in the previous slide, the relation between the Cp and Cv. Before this slide we are understood this Cv is a du by dt. So you can write du is equals to Cv into dt, and that's why for m kg of mass you can write q is equals to u plus mcv dt, and this is the equation for heat transfer for constant volume process or isochoric process. So we have a mainly three relation: PVT relation, work done relation, and heat transfer relation, and it is important as per the calculation of example. Now the second process is isobaric process. Isobaric process. So isobaric process is the process in which the pressure is constant. The pressure is constant, it means that the pressure at any point, at point P1, at point P2, at point P3, or any point P, the value of the pressure is become constant. It does not change. So let's start with this PVT relation. So if we write the PVT relation for PVT relation for isobaric process. So we know PV is equals to MRT. So PV upon T is equals to constant. So if we write this term, P1 V1 upon T1 is equals to P2 V2 upon T2. But here we know P1 is equals to P2. So you can remove this, cancel this. So V1 upon T1 is equals to V2 upon T2. That's why we can write over here V1 by V2 is equals to T1 by T2. So this is the relation of V and T in isobaric process. Now second one is a work done relation. So for the work done relation, we know W is equals to integration 1 to 2 P dV. So here pressure is constant, so P does not integrate, so we can write P outside of the integration 1 to 2 dV. So if we integrate this value, then we get P into V2 minus, if we integrate this dV, then we get V and put the limits V2 minus V1. So we get this equation. If we multiply the P inside the bracket, then P V2 minus P V1. But here for the isochoric process, we know P is nothing but it is P1, P2 or P3, anything, you can write anything. So here we replace the P with the P2 into V2 minus, here the P is replaced with the P1. So I write P1 V1. But here for as per the gas characteristic equation, PV is equals to MRT. So I can write MRT2 minus MRT1. I cannot write over here M1 R1 because it is a constant value, that's why. So if we common this MR, then the equation is T2 minus T1 and W. So this is the equation for work for the isobaric process. Okay, so MR T2 minus T1. Now third one is a heat transfer. So for the heat transfer, we know first law of the thermodynamics, FLT, it is dq is equals to du plus dw. So we can write over here u2 minus u1 because it is change in internal energy, plus also we can write this equation du plus change in pressure and volume. So if we write this equation, then it comes over here P2 minus P2 V2 minus P1 V1 for isobaric process. If we rearrange the terminology, U2 plus P2 V2, take the common minus from the both terminology. So here it is U1 plus P1 V1. That's why we can write over here H2 minus H1 because enthalpy relation is U plus PV. Okay, so here you can write over here dq is equals to dh, and we know the relation of Cp is equals to dh upon dt. So I write over here it is Cp dt, or we can write for total H is equals to, or Q is equals to m Cp dt. So this is the relation between the heat transfer in isobaric process. Okay. Now here the dq is equals to m Cp dt, but here we know the relation of the Cp, gamma and R is equals to Cp is equals to gamma into R upon gamma minus 1. If you put this relation in this value, then m Cp is the gamma into R upon gamma minus 1 into change in temperature T2 minus T1. So this is the relation of heat transfer, final relation of heat transfer for isobaric process. Now the third process is isothermal process. So isothermal process, we'll discuss with the isothermal process. In isothermal process, temperature is remained constant. The temperature is remained constant. The process in which the temperature is remained constant, it is called isothermal process. So we can write over here T1 is equals to T2 is equals to T3 is equals to T is equals to constant. So first let's derive with the PVT relation, pressure, volume and temperature relation. So pressure, temperature and volume relation, we can write over here PV is upon T is equals to C as per the gas characteristic equation. So we can write P1 V1 upon T1 is equals to P2 V2 upon T2 is equals to PV upon T is equals to constant. So you can write in that way, but here the temperature is constant, so you can remove it. Then we get the value over here is P1 V1 is equals to P2 P2. That's why we can write over here P1 by P2 is equals to V2 by P1. So this relation for isothermal process, PVT relation. Now second one is a work done equation. So work done equation for the isothermal process, we can write over here dW is equals to 1 to 2 PdV, integration of 1 to 2 PdV. So here from this equation PVT is equals to C, P1 V1 upon T1 is equals to C. We can write over here P is equals to from this equation P is equals to, or we simply says that here T is a constant, so we can remove it. So P is equals to P1 V1 upon V from these two relation, first and third one, P1 V1 upon T1 PV upon T1, T is a cancel out, so P1 V1 is equals to P into V. From this relation we can write P is equals to P1 V1 upon V. So put this value in this equation. So if we put this value, then integration 1 to 2 we can write over here P1 V1 upon V into dV. Okay, but here the value of pressure and volume at particular one point is fixed, so we cannot integrate it. So P1 V1 integration of 1 to 2 1 upon V dV. If you integrate this total value, then we can find over here P1 V1, it is nothing but it is ln or log, the value is log E base V, and the value of or we can say the limit is 1 to 2. So if you write this relation P1 V1, then it is log E base V2 minus V1. If you write this term, then P1 V1 is equals to log E base. If there is a log and here it is a minus, then we can write V2 by V1. Okay. Also we can write this relation PV is equals to MRT. So we can write from here PV V1 is equals to MRT1 log E base V2 by V1. And also we can replace this V2 by V1 by P1 by P2. So also we can write this equation MRT1 in form of pressure, and it is P1 by P2. Okay, log E base. So this is the relation of work done for isothermal process. I write over here it is MRT1 log E base V2 by V1 is equals to MRT1 log E base P1 by P2. And you need to remember this relation for exam point of view or to solve the examples. Work done for isothermal process we can write in that sense. Now third relation is Third relation is heat transfer. So heat transfer for isothermal process. So as per the first law of thermodynamics, dq is equals to du plus dw. But here we know at constant temperature, if the temperature is constant, the change in internal energy, U is nothing but it is internal energy, and its values become 0. For constant temperature, in any constant temperature process, the change in internal energy becomes 0. So we put over here dw is equals to, sorry, du is equals to 0. So we can write this relation dq is equals to dw, and that's why here we already derived dq is equals to p1 v1 log E base v2 by v1, or we can write over here p1 v1 log E base p1 by v2. So this is the relation for heat transfer and work done. So simply we says that for isothermal process dq is equals to dw. So you need not to require to write down the or to calculate the both things in separately, but whatever the dq is there, it's equals to dw, because change in internal energy becomes 0 for isothermal process. So this is the all three process. We start with the isochoric, then isobaric and isothermal, and we relation establish PVT, heat transfer and work done. Now let's start with the fourth one, and it is very important. So I write on the new page, and it is the fourth one is a reversible process, reversible adiabatic process. So reversible adiabatic process is a process in which the heat transfer is become 0. Heat transfer is 0. Sorry, adiabatic process. It is called adiabatic process. So for adiabatic process, we want to derive over here the PVT relations and heat transfer relation and work done relation. So let's start with the PVT relation. So first PVT relation, and here it is very important. But before going to start with the PVT relation, for the adiabatic equation, here the equation PV raised to gamma is equals to C. We can write this equation. We derived this equation, and you already know this equation. This is available in the book if you want to see it, or you can derive directly from, you can see this directly from the book. Okay, so we can write over here P1 V1 raised to gamma is equals to P2 V2 raised to gamma is equals to P V raised to gamma is equals to C. So this is the elaboration of this equation. So let's start with this PVT relation. So P1, we know P1 V1 raised to gamma is equals to P2 V2 raised to gamma is equals to PV raised to gamma. So here we can rearrange these two terms. Then we can write over here P1 by P2 is equals to V2 by V1 raised to gamma. Okay, these two terms. P1 by P2 is equals to V2 by V1. Common, we can say V2 by V1 raised to gamma. Power is common, so we put on both the term. Now, here, this is the equation number 1 I put. Now we have a gas characteristic equation P1 V1 upon T1 is equals to P2 V2 upon T2. So from this relation we can write over here the P1 by P2 is equals to P1 by P2 is equals to, I put this on top side, so T1 by T2 and V2 by P1. So from rearranging this term, we get the P1 by P2 value over here. So now put this value, put P1 by P2, put P1 by P2 in equation number 1. Equation number 1. So we get this equation is T1 by T2 into V2 by V1 is equals to V2 by V1 raised to gamma. And over here the T1 by T2 is equals to, here I try to put this value in denominator, so we can write V2 by V1, and here we know it's our 1 power. So we can write this V2 by V1 raised to gamma minus 1. So this is the final relation between the temperature and volume. T1 by, right over here, T1 by T2 is equals to V2 by V1 raised to gamma minus 1, and this is the relation. This is very important relation. Note down this. Now this is the relation between the temperature and volume. Now I try to establish the relation between in form of temperature and pressure. So let's start with this. So if we write this thing, then we already know here this equation, and from this equation I try to write V1 by V2 is equals to V1 by V2 is equals to V1 by V2 is equals to P2 by P1 1 upon gamma. Okay, from this relation I write over here this thing. V1 by V2 is equals to P2 by P1. The power of this V1 by V2 is inverse and right over here. So V1 by V2 is equals to P2 by P1. P2 by P1. So I write over here in proper way. V1 by V2 is equals to P2 by P1 raised to 1 upon gamma, and this I put over here the equation number 2. Now here we had this relation. I write this relation in form of V1 and V2. So if I try to write this equation in form of V1 and V2, then V1 and V2 is equals to, from this relation, V1 by V2 is equals to P2 by P1, P2 by P1. I put this over a denominator and T1 on upper side, so T1 by T2. Put this equation in, put value of, put V1 by V2 in equation number 2. So you get over here the P2 by P1 into T1 by T2 is equals to P2 by P1 1 upon gamma. I write over here this terminology. T1 by T2 is equals to 2 by P1 1 upon gamma. I write this P2 by P1 on denominator, so P2 by P1. So I can write the base is common, power 1 upon gamma minus 1 because power is minus. That's why I write over here T1 by P2 is equals to P2 by P1. Take the LCM for this, so value is 1 minus gamma upon gamma. Okay, so this is the relation which we are established for the same. Also we can write the D1 by T2 is equals to P1 by P2. If we change this value from denominator to, so right over here gamma minus 1 upon gamma, because here common is minus, and that's why the final relation is established this one. So here in PVT relation we have three main equation. One is a PV raised to gamma is equals to C. Second one is a T1 by T2 is equals to V2 by V1 raised to gamma minus 1, and third one is a T1 by T2 is equals to P1 by P2 raised to gamma minus 1 upon gamma. So this three relation is very important for us. So note down this three relation for the adiabatic process or reversible adiabatic process. So here the PVT relation part is over. Now second part is the work done relation. So work done relation. So work done as per the first law, we know the work done is equals W is equals to 122 PdV, So we already know the PV raised to gamma is equals to C. So we can write P1 V1 raised to gamma is equals to P2 V2 raised to gamma is equals to PV raised to gamma is equals to C. So from this and this equation, we can write over here P is equals to P1 V1 raised to gamma upon V raised to gamma. Put this P value in this equation. So we get 1 to 2 is equals to P1 raised to gamma upon V raised to gamma into dV. But here the P1 V1 for particular point the value is constant, so we cannot integrate it. So write over here P1 V1 raised to gamma 1 upon V raised to gamma into dV. And then after, if we integrate the whole value and solve this equation, if we integrate and solve above equation, then we find the value of work done is equals to P1 V1 minus P2 V2 upon gamma minus 1. That's why we can write over here PV is equals to MRT. So MRT1 minus MRT2 upon gamma minus 1. So if we take the MR common, then M into R upon gamma minus 1 into T1 minus T2. So this is the relation of work done for the reversible adiabatic process. Or we can write over here dQ is equals du is equals to dW, because dQ, we know the first law of thermodynamics, dQ is equals to du plus dW. But here for the adiabatic process this value is 0. So I can write over here dW is equals to minus, or du is equals to minus dW. So I can write this relation, du is equals to minus mr T1 minus T2, sorry, gamma minus 1 into T1 minus T2. So finally we have a du is equals to dW is equals to mr gamma minus 1 into T2 minus T1. How it will come? Here the minus sign, I change this sign, T2 minus T1, minus common, so we get this final relation of work done and internal energy. So this is very simple to understand the things which we are studying over here, and it's very simple. So if you summarize the whole all the parts, then you can understood. So write in your notebook all the relation, PVT relation, work done relation, and heat transfer relation, internal energy relation for the all four. Okay, now the next is a TDS relation. TDS relation, it is very important. We know the first law of thermodynamics, and it is dQ is equals to du plus dW, or P into dV. And also for the reversible process, we can write the entropy ds is equals to dQ upon T. If we rewrite this equation, then dQ is equals to ds into T. Put this dQ in this equation, so we can write T into ds is equals to du plus P into dV. I'll put this equation number 1. Now we have one more equation for enthalpy, H is equals to U plus PV. If we differentiate this equation, then we get the value of dH is equals to du plus PdV plus VdP. Here we differentiate PV, so P is a constant, differentiate of V is dV. Second time V is a constant and differentiate of P is the dP. So I write in that way. But here we know du plus PdV, this equation it is over here, du plus PdV. So from equation 1 we can write over here dH is equals to TdS plus VdP. If I rearrange this term, then TdS is equals to dH minus VdP, and I put over here, this is the equation number 2. So we have a two equation, TdS du plus PdV and TdS dH minus VdP. Now from the first equation I try to write over here, ds is equals to du upon T plus PdV upon T. Here I try to try to divide the whole term by temperature on both sides. So temperature after cancel out, here du upon T and P by T into dV. So I get this value. But we already discussed in the previous slide, that is the definition of du, and du is nothing but it is a Cv into dt. In the relation of Cv and Cp, we know the du is the relation of Cv is du by dt, and the relation of Cp is dH upon dt. So I write over here dH Cp into dt. This already discussed in the previous slide. If I put over here the value of du in this equation, and also we know the PV is equals to R into T. So if I put over here P by T is equals to T put on denominator, then I write over here R upon V. So if we put the du and P by T value in this equation, then I write the term ds is equals to Cv dt upon T plus R upon V into dV. Okay, now integrate this term. If we integrate this equation, then ds Cv is constant, so it is 1 upon T dt, integration is 1 to 2 for limit, plus R upon V, so R is constant, 1 to 2, 1 upon V into dV. So here if we integrate S, then it is S 1 to 2 Cv. Here we know the 1 upon T is a log or ln E base T, sorry, and limit is 1 to 2 plus R into V, it is log E base V. Integration of 1 upon V is ln V or log E base V, and the limit is 1 to 2. If we apply the limits, then this values become S2 minus S1 is equals to Cv log E base T2 minus T1 and plus R is equals to log E base V2 minus V1. Okay, so if I write this equation in log E base T2 by T1 plus R into log E base in form of, this is not T1, it is V1, V2 by V1. So this is the first equation. Okay, S2 minus S1, change in entropy in form of temperature and volume. Okay, and it is a very important equation for exam point of view. Now take the second equation, this equation, and try to put over here. Here I write over here ds dH upon T minus V upon T into dP. Put the value of dH from here. So here you can take the value Cp dt by T minus V by T. So from PVT relation, this is the, if V by T, and this relation is, we can write also the V by T is equals to V by T is equals to R upon P. So we have a two equation, one is a dH and second one is a V by T. If you put over here Cp dt by T and V by T is your R upon P into dP. Okay, ds is equals to this. Now next time we have to need to require integration. So if we integrate this equation, then we get the value over here S2 minus S1 is equals to Cp log E base T2 minus T1, so T2 by T1 minus R log E base P2 by P1. So here the main two equation in form of pressure and temperature and volume and temperature of this TDS relation in form of entropy. So this two equation is very important, and it is asked in the examination to find out the value of delta S or change in entropy. The whole parameters is given. So for to solution the example, this two equation is very important. So remember these two things in your mind. Now let's start with the example. Here the first example is GATE 2018 session 1. So here the example of ideal gas. So in the example, ideal gas undergoes the process. State 1 is given and state 2 is given. The specific heat of ideal gas is given, Cp and Cv value is given, and you need to find the specific entropy for the ideal gas. So here I do not write to all the datas, just solve the problems, and it is very easy problem. So answer is for this problem is, here we already discussed in the previous slide the TDS equation, in which we derive from the TDS relation. We already derived this thing, the two equation. One is a delta S or S2 minus S1 is equals to Cp ln or log E base ln T2 by T1 minus R ln P2 by P1 R ln P2 by P1. Or second one equation is S2 minus S1 is equals to Cp ln T2 by T1 plus R ln V2 by V1. So here in the given example, we have a temperature and pressure. We do not have a volume. So we are directly go with this first equation, the first relation. Okay. And here the value of Cp and Cv both are given. And we also know the relation R is equals to Cp minus Cv. So here the Cp is given 1 and Cv is given 0.7. So you get the value of R is 0.3 kilojoule per kg into Kelvin. Okay. And the value also other values are given. So let's start with the find the value of specific entropy. Delta S is equals to Cp. Cp is 1 kilojoule per kg into Kelvin. Then after we had ln T2. T2 is given 600 Kelvin divided by T1. T1 is given is 300 Kelvin minus R value. R value is we already calculated 0.3 ln P2 is given over here is 500 kilopascal. So I write over here 500 divided by P1 is given 100 kilopascal. If I calculate this thing, try to calculate, I will give you some time. So if the calculation is done, then the answer for this is delta S is equals to 0.21 kilojoule per kg to Kelvin. So here you can see the very basic example is asked in the GATE, and this is the first example 2018 for the set 1. So here only if you observe this example, then only the required thing is this equation and this relation. So previously we already do the practice and already derive this relation, so you need to must remember this thing. You can easily solve the example. Now let's start with the second one. So here the second one example is 2017 GATE session 1. So here the molar specific heat. So here direct value is not given, here value is given in form of molar molecular weight. The specific heat at constant volume of ideal gas. So ideal gas specific heat of constant volume equals to 2.5 times the universal gas constant. So its value is 2.5 times the universal gas constant, and its universal gas constant value is 8.314 joule per mole into Kelvin. When the temperature is increased by 100 Kelvin, so change in temperature is given and it is 100 Kelvin. So you need to find the molar specific enthalpy. Okay, so here if you write the given data, then here my answer is for that is specific heat at constant volume. So CV is equals to 2.5 times the universal gas constant, and we know the value RU. Okay, and here the value of RU is given and it is 8.314 joule per mole into Kelvin. Okay, second thing is given the change in temperature. So change in temperature is equals to 100 Kelvin. Okay, and you need to find the delta H, change in enthalpy. So here in the previous slide we already discussed the specific heat at constant pressure and specific heat at constant volume. At that time we discussed the Cp is nothing but it is delta H upon delta T, and Cv is equals to delta U upon delta T. So we already discussed in the previous slide these two things. Same things we need to use over here. So we need to use delta H. So for delta H we had an equation delta H is equals to Cp into delta T. Okay, so here the Cp is not given, Cv is given. So try to convert this Cv into Cp. So how we can convert it? We know the relation Cp minus Cv is equals to R. So gas constant. But here the value is given for a molar specific heat, molar. So when you multiply this R with molecular mass M, then it's become Ru. So this value is given, specific heat value is given, molar value, not in kilojoule per kg, it's in molar kg. So that's why we need to multiply with the molar mass or molecular weight. So this value is become Ru. So we had a Cv value and it is 2.5 Ru, and this value is also become Ru. So that's why the value of Cp it is 3.5 universal gas constant. So this value is here, and the change in temperature is given. So and here the Cp is there. So Cp is equals to 3.5 Ru into delta T, and here the 3.5 into Ru is a universal gas constant, and this value is already given 8.314 joule per mole into Kelvin. So I write over here 8.314 into change in temperature, it is 100 Kelvin. So if you calculate the whole value, then you find the answer, and answer is so value is 2909.9 joule per mole. So this is the value of delta H. So I write over here delta H is equals to 2909.9 joule per mole. This is our answer, final answer. So example is very simple. Only if you understand the theories, or if you know the theories, then you can get the easily answer. So this is asked in the 2017 session 1. Okay, so it's very simple. So whatever the theory you are studied, you can implement over here and you can find the value. So it's very simple. Now let's start with another example. Here the example number 3, 1 kg of ideal gas. So 1 kg mass is given and ideal gas is there. So R value is given for that, joule per kg into Kelvin. Specific heat at constant volume. So CV is given, it is 1000 joule per kg into Kelvin at 1 bar and 300 Kelvin. So pressure and temperature both are given. Okay, it's contained a sealed rigid cylinder. So this ideal gas is filled in the rigid cylinder. Okay, and during the adiabatic process, here the adiabatic process is carried out on this gas. 100 kilojoule of the work is done, and they are applied the 100 kilojoule work on the system. So on the system by the stirrer. Okay, so how much entropy is generated or increase we need to find. Okay, so it's very simple. Here the data is given in that way. Here, if you consider this is the rigid cylinder, so here it is a rigid, okay, rigid cylinder, and here it is a stirrer is applied. So switch stirrer is rotated and some amount of, we can say, energy is used, and here it is rotated, which we are applying the work 100 kilojoule. But here we are supply the work to the system. If you consider this is a system, then we know the work is minus. So here I write over here answer given data. So first I write over here work is minus 100 kilojoule. Okay, why this is minus? Because we are giving the work to the system. That's why we are put minus, because we already know the thermodynamics terminology. If any system, if the work is entered to the system, we are taking minus. If we work out from the system, then we are taking positive. Same thing, if we heat enter to the system, we are taking plus. If we heat leaving to the system, then we are taking negative. So this is the scenario in the thermodynamics. And here the other things is given, the pressure is given, and pressure is 1 bar, temperature is given and it is 300 Kelvin. Also the mass of the gas is given 1 kg, and value of R is given 400 joule per kg and Kelvin. Okay, so you need to find the value of delta S, change in the entropy. Okay, so here we already know for TDS relation, we already derived this equation, TDS relation, where we know the S2 minus S1 is equals to mCV ln T2 by T1 minus, plus over here we are taking for volume m R ln V2 by V1. So this relation already we discussed in the previous slide. Okay, in TDS relation, this form TDS relation. Okay, we need to use this relation. So here if you see this relation, then you find something that here the cylinder is rigid. Here you need to understand the rigid cylinder. So if the cylinder is rigid, it means that the volume of the gas does not change. So V1 is equals to V2. Volume does not change because rigid cylinder, and that's why this value is 0. So we have a final equation of change in volume is m CV ln T2 by T1. Okay, this is equation which we need to use to find the entropy. But here we have a initial pressure P1 and temperature is given, but we don't know the T2. Also the CV is also given, and CV value is 1000 joule per kg into Kelvin. Okay, so we have M, CV, Ln, so T2 and T1. T1 is there, but T2 is not there. So we need to find the value of T2. How we can find the value of T2? So let's check. So we need to use the first law of thermodynamics. dq is equals to du plus dw. Okay, but here you can see here the adiabatic process is carried out. So when the adiabatic process is carried out, the heat transfer is become 0. So for the adiabatic process, dq becomes 0. Change in heat or heat transfer is 0. So this value is become 0. So your equation is become du is equals to minus dw. Okay, but here for the such a process, we know the equation of change in internal energy, and the equation for the change in internal energy is sorry for disturb. Here we know the value of sorry for interrupt. Sorry for disturb over here. So here we know the du is equals to minus dw. So we can write over here mcv T2 minus T1. This is the thermodynamics process in which we already derived these things: internal energy, heat transfer, PVT relation and work relation, and at that time we derived this value. So you can find from in previous slide. And also the minus dw value is given here, the work done. The dw value is given, it is minus 100. So I put over here minus 100. Okay, so from this, if you put the value of m is equals to 1 kg, cv is equals to 1000, and T2 we need to find, T1 we have 300 Kelvin, and here it is plus 100. Now if I calculate the whole values, then we find the value of T2, and T2 is 400 Kelvin. We get the value of T2 is 400 Kelvin by solving this equation. Okay, so here it's very simple. This part you need to understand. So now we want to find the delta S. So mass is 1 kg, CV specific heat is 1000, Ln, T2 we have 400, and T1 we had 300. Put the value and calculate it. So try to calculate it. So if you calculate, then value comes around 287.68 kilojoule per kg into Kelvin. Sorry, here it is not kilojoule, it is joule per kg into Kelvin. So this is my final answer for this problem. So here you can understood how the theory works. If you know the equations in better way, you can implement it in the example and you can easily find the values. So it's very simple to understand. So let's move to the example number 4. So here the example number 4 is from 2017 GATE part 2, session 2. Here it's given the mass of M, perfect gas, pressure, initial condition is given, pressure P1 and V1, undergoes a isothermal process. So process is given isothermal process. Okay. The final pressure, so P2 and V2 pressure is given. The work done on the system is considered positive. If the R is the gas constant and T is the temperature, the work done on the process is. So you need to give the value of work done or equation of the work done for the isothermal process. And if you see the previous slides, then we already derived these things in our previous session in isothermal process work done relation. So let's dive with the another time next. So here we know the work done is equals to dW is equals to integration 1 to 2 PdV relation. Okay, from this equation we derive the equation of work done for isothermal process. But here we know PV is equals to MRT, so PV upon T is equals to constant. So we can write this value P1 upon V1 upon T1 is equals to P2 upon V2 upon T2 is equals to P into V upon T is equals to constant. So this is the PVT relation from the VVT relation, but here T1, T2 and T is constant. So the isothermal process, we know for isothermal process T1 is equals to T2 is equals to T3 is equals to T. Okay, so that's why I write over here. So from 1 and 3 equation I can write over here P is equals to P1 V1 upon V. Put this value in this equation. So 1 to 2 P is equals to P1 V1 upon V into dV. So now if we take the integration, okay, so we know the P1 V1 is a constant, so come outside and integration 1 to 2 1 upon V into dV. So if we integrate this value, then we know this is the ln V2 by V1. Okay, so this is the equation for a work done for isothermal process. This is the one equation. Second, if you modified this equation, also you can write in that format. Here from this, if you see P1 V1 is equals to P2 V2. So here V2 by V1 is equals to P1 by P2. So you can also write this equation in that format, P1 V1 ln P1 by P2. So this is the another equation in form of pressure, and here it is in form of volume. So maybe it is directly, if you know this equation you can write in the example. If you don't know, then you need to understand how we can derive this equation from the theories. So theory is very important part. So when you start for preparation, you need to always understand the theory, so you get the all the examples in quick time. So now next example number 5, which is from the GATE 2017 set 2. Here the volume and temperature of the air is in a closed vessel is given, and the volume is 2.87 meter cube and temperature is 300 Kelvin. The gauge pressure indicated by manometer fitted to the wall of the vessel is 0.5 bar. Here gauge pressure is given, and then after, if the gas constant is 287, okay, so here the value of R is given 287. Here it is not, but please check. Sorry, joule per kg into Kelvin, and atmospheric pressure is 1 bar. Atmospheric pressure is given 1 bar. We need to find the mass of air. So the example is very simple. Here I write over here solution. So given data, first we had a volume V and it is 2.87 meter cube. Then temperature T and it is 300 Kelvin. And pressure, here the gauge pressure is given, so I write over here PG gauge pressure, and its value is 0.5 bar. Then after, the value of R is given, and it is 287 joule per kg into Kelvin. and here the atmospheric pressure given. So P atmosphere, and the value is 1 bar, and we need to finally find the mass. So you can see from the data here whatever the values are given, pressure, volume, temperature, and R, you need to find the M, mass. So from the given data you can identify the gas. Here we can use easily the gas characteristic equation to find the value of M, because whatever the given data we can easily identify our solution. So we can use the PV equals to MRF equation and directly find the value of M from the given data. So before we start, here the two pressures is given. Here is P gauge and P atmosphere. So let's find the P absolute. So we know the P absolute is equal to P gauge plus P atmosphere. So total pressure is 0.5 plus 1. So here this value is 1.5 bar. Okay. Now from the gas characteristic equation, V is equals to mRT, and that's why M is equals to PV upon RT. So if you put the value, pressure is equals to 1.5, P volume is given 2.87 meter cube, R is given over here 287, R is given 287, and temperature is given 300 Kelvin. So here it is a given data, but here the pressure is given in bar. We need to convert in Newton per meter square. So here we need to multiply with 10 raised to 5. So it is now converted into Newton per meter square. Okay. Now if you calculate, if you get the answer, this problem is mass is 5 kg. M is equal to 5 kg. So this is the final answer of this problem. So if you observe the whole example, the example is very simple. The main things is here one equation P is equals to MRT, and second thing is we actually gauge the atmosphere, and the whole equations are given. We put the values and get the answer. So it's very simple to understand. Okay. So now let's start with the next example, and here it is example number 6. Here is the example from 2007-28. Set number 2. The given data: 1 kg of ideal gas, mass is given 1 kg, ideal gas, R value is given 287. Irreversible process are there. State 1, so pressure is given 1 bar and temperature is given 300 Kelvin. For state 2, the pressure is 2 bar and temperature is 300 Kelvin. And here you need to find the specific entropy, change in specific entropy, S1 minus S2 of the gas. Okay, so the very basic, we can say a simple example. So let's start with the answer, solution of this. And given data, I write over here first of all, given data. So in given data, we are R value is 287 Joule per kg into Kelvin. For state 1, pressure P1 is given 1 bar and temperature T1 is given 300 Kelvin. For state 2, pressure P2 is given 2 bar and temperature T2 is given 300 Kelvin. So here you can observe the temperature in the both states are same. So T1 is equals to T2, so it becomes isothermal process. So thermal process. Okay, and it is irreversible process. So irreversible isothermal process. And we need to find over here S1 minus S2, delta S value into 5. Okay, so this is a very simple example. We already know these things. We know the equation for delta S. Delta S is equals to delta Q upon T, change in heat upon temperature. But for isothermal process, if you know the equation of heat transfer in the previous slide, then you find the value of delta Q is equal to delta W equals to N, sorry for interrupt. Here the value of delta Q is N R T1 ln T1 by T2. This is the equation for isothermal process. In this temperature is T1. Okay, cancel out. How it is come? From previous slide, isothermal process. Remember this thing, isothermal process in which heat transfer, second equation, heat transfer dQ is equal to du plus dW. Therefore, isothermal process, this value is 0, and that's why dQ is equal to dW, and this equation is come mRT ln T1 by T2. You already discussed this things in the slide. So from the same we get over here, and the value of M is given 1 kg, R is given 287, ln is given 1 by 2, 1 T1 by T2 and T1 already. So if we calculate it, then we get the value of delta S. So by using the calculator, we can calculate it and find the delta S, and value is minus 198.93 in joule per kg into Kelvin. Here I am not much more discuss for the units, because you know the units of all the parameters. You are ready for get. So this is very simple things where you need to convert some unit conversion. So this is easy to understand and you already know. So I am not discuss this part over here. So here the value of delta S we get from this equation. So very simple part. Now let's start with the next one. Here it is the example number 7. So in the example number 7 is from 2016 GAT. Set number 1. So here it is also ideal gas. A reversible process is there. Pressure is varies linearly. So pressure varies linearly with volume and the condition of the start point and end point. So T1, substitution 1 and 2. Its value is given. So really we have given data. P1 is given, B1 is given, P2 is given, B2 is given, and R is given. Here you need to find the value of work. Okay. So all the data are given. So how we can use the, or how can find the value of work over here? Because here the process is a reversible process. First of all, this thing we need to understand. And second is pressure is varies with the volume. Here the pressure is supposed to vary with the volume. So P inversely V. The pressure is increased, volume is decreases, and here you can see from the given data, the pressure is 100 kilopascal, the volume is 0.2. Pressure is increased to 200 and volume become half. So we can say it is decreased by we can say 50%. So here we have a simple equation of the work done, and it is PdV, pressure into change in volume. But here the pressure you cannot say directly P1 or P2, but here we are taking the average pressure, because the pressure values it becomes half. So P1 is equals to 100 and P2 is equals to 200 divided by 2. So 300 divided by 2. So this value becomes 150 kilopascal. So put the value 150 kilopascal, change in volume. Volume is given 0.2 minus 0.1, change in volume, V1 minus V2. Again, write over here is V1 minus V2 or V2 minus V1. So 0.1 minus 0.2. So that's why the total value whatever we are getting over here is minus 50 kilojoule work. The value become minus. Negative sign indicate it is compressive work. Compression process is take place. So compressive work. That's why here sign is minus. So very simple example. You can understand that here from this given information. Now next here example number 8, and from the example number 8 you can see this example is from GATE 2016 set number 2. Here the piston and cylinder initially the contents 0.4 meter cube of air, and it has the ideal gas. So ideal gas is given and the pressure and temperature is also given. Now it is isothermally compressed, so temperature is remaining constant and volume is 0.1 meter cube. We need to find over here work done during the process. So here we have to find work done. Okay, so the same example is a very simple example, but here the piston and cylinder, and here ideal gas is given, so we can directly use the equation of ideal gas, and we know the equation for here process is isothermal process. So for isothermal process, the equation of work done dq is equals to du plus dw, but here we know du becomes 0, so dq is equals to dw, and the equation for work done over here, if we integrate it and prove the value, then we get P1 V1 ln V2 by V1. This expression we already derived in the previous slide. You can refer the previous slide and get this equation. So now put the value. So for state 1, the value of pressure is given 100 kilopascal. So put over here 100 kilopascal. And the volume is given 0.4 meter cube. So put over here 0.4 meter cube. ln V2 is given over here after compression is 0.1 meter cube. So put over here 0.1 divided by V1 0.4 meter cube. This value is taken. So W is equals to over here. If we calculate the whole value, then we get answer is minus 55.45 kilo, and this is the answer for work done for compressive work which are carried out by the piston and cylinder. Here the also the negative sign, and the negative sign is there the compressive work. Compressive work is already given in the example. There is a sign convention. So you can write over here. If you want to write over here the compressive work, 55.45 kilojoule work, but here you can write compressive. Okay? So you can remove the sign convention, but you need to write over here compressive work. So it is very simple example. Based on your theory, you can calculate the each and every example in separate manner. So let's start with the next example. The example number 9. Okay, it is a good example actually, and it is asked in the 2015 GATE. This is set number 1. So let's start with this example number 9. Temperature of the nitrogen in the vessel of volume 2 meter cube, 288 Kelvin. A U-tube manometer connected to the vessel from the reading 70 centimeter of mercury. So I think height is given. Thereafter, the universal gas constant is given 8314 joule. Atmospheric pressure is given. Okay, acceleration due to gravity. So value of gravity is given. G value is given. Density is given. Nice thing. Density is given, and you need to find the mass of the nitrogen. So let's collect the data. So from the given data, we can write over here the volume is given, and volume is 2 meter cube. Okay, temperature is given, so write over here temperature is 288 Kelvin. Okay, Then after we write over here the height of nanometer is given. So height of the nanometer is given, and its value is 70 centimeters. Right over here the height of gauge, it is 70 centimeters. Okay, then after Rg, universal gas constant is given, Rg, and its value is 3317 joule per mole into Kelvin. Okay, atmospheric pressure is given, so P atmospheric given, it is 1.01325 bar. Second important thing is given is G, that acceleration due to gravity, and it is 9.81 meter per second square. And then after density rho is given 13600 kg per meter cube. And here you need to find mass of nitrogen. So this is the given data which are available with us. So first of all, the atmospheric pressure given. So here we required absolute pressure. So we know absolute pressure is equal to gauge pressure plus atmospheric pressure. So first of all, we need to find the gauge pressure, and the gauge pressure is here in gauge, calculate over here, into rho into G into H of gauge. Rho is given 13,600, 9.81, and Hg is given in centimeter, that is 70 centimeter. But here you need to convert it into meter because all the parameters are in meter. How many parameters? G meter, density, kg per meter cube is also in meter, so we need to divide with the 100. So if you calculate the whole calculation, then you get the answer of Pg, and Pg value is 9391.2 Pascal. Okay, and here the value of atmospheric pressure is given, it is 1.01325 bar. So if you convert into the Pascal, then you get value 1013255 Pascal. Okay, so put over here the both the values, we need to find in the P absolute value, and you get the total value of pressure is 194,716.2 Pascal. I have put over here the value in Pascal. The reason behind that is here we had a temperature and pressure in meter, so ultimately we need to convert it into the Pascal. The final answer is kg. Okay, and also the some other reason, so we are taking into Pascal, so easy to calculate. Now second thing, we know here we want to require find the m, we need to require the equation, simple equation, gas characteristic equation, Pv is equals to m r t. Okay, so m is equals to p into v upon r into t. Okay, so p with us, okay, p is here, volume is given, so volume is 2 meter cube, volume is given, r is there, P is there, temperature is also given 288 Kelvin. But the problem is over is R, because here R is not given, but here the given value is Rg. Okay, so here we know the universal gas constant Rg is defined as it is the product of R gas constant into molecular mass n. So if you want to find from this equation the value of R, then it is the value of R, it is Rg by m. What is the Rg? Rg is given 8317. Okay, and molecular mass of the nitrogen. So if you remember the molecular mass of the nitrogen, the value of N2 or mass of nitrogen, it is 28. Okay, so divide with the 28 and you get the value of R. Okay, so from here you can find the value of R. So let's start with the calculation of the mass. So P is given and its value is 1947162. And the volume is given 2 meter cube into R. R is we need to calculate, so I put over direct value 8317 upon 28, and temperature is given, and temperature is 288. Okay, so from this you can find the mass, and the value of the mass for this example is mass of nitrogen is 4.55 kilogram. So here it's very simple to calculate, but the most important equation for here is where we absolutely need to know where the use of this universal gas constant equation. We can find the value of V in this equation, and finally the gas characteristic equation P is equal to L. So it's basically very simple to calculate, but the fundamental of the thermodynamics you know, and you can easily calculate. Now let's start with the example number 10. Here the some complication are there, some interesting examples we can say over here. It's from the GATE 2015 stat number 1. So here is given it is a well insulated rigid container. So when you see the insulated rigid container, means volume is constant, volume is does not change. Yes, these things we need to understand. Whenever the rigid container is given and its volume is does not change. Okay, so the given volume is 1 meter cube. So write over here the given data. Write over here the given data, and I simply write that volume is 1 meter cube. Okay, mass is given, and mass is 1 kg. Okay, ideal gas, and ideal gas Cp is given 1000 joule per kg into Kelvin, and Cv is given 800 joule per kg into Kelvin. Pressure P is given 105 pascal, and here stirrer is given inside this insulator. The stirrer is rotated at constant RPM in container 1000 rotations. Okay, so here the rotations is given, and it is 1000. Right over here with the W rotations in RPM, or you can write in N. W by N. Normal notations is given for RPM is N, and then after torque is given. Torque is applied. The torque is 100 Newton. And here you need to find the final temperature for this container fluid. So the example is very interesting because so many things are given. So you already discussed the example in the previous slide. There is one container, inside that there is one stirrer. Stirrer is rotated with the help of some applied force or applied torque with some RPM. Okay, and you need to find after the rotation what is the temperature of the fluid inside the container. This thing is going to find. So let's start with the basic thing. So here the N and T is given. So from that, here directly work is not given. If the work is directly given, then we can easily calculate the answer. But here the stirrer work we can need to find. So stirrer work we can find W is equal to 2 pi. Okay, 2 pi N. The work you can find it this way. So the value of 2 pi N, and this value is 2 pi N into plot P. This equation we already used. Here for joule, if you want to convert into joule per second, then divided by 60. Okay, so 2 pi N, total work I need to find. 2 pi RPM is given 1000, and temperature is given 100. So by solving this, we gave the value of stirrer work, and its value is 628. Sorry. Sorry. So value for the W is 628 3185 joule. Okay. Here we calculate the answer W in joule. If you want to calculate the watt, then divide with the 60. W by NT by 60. Okay. So this is the Taylor law. Now we know the equation of heat MC delta T. So M, here the value of constant volume because resistor. So take over here is CP, CV and delta T. Okay. So this is the equation. But the process in which the heat is transferred and the container is insulated. So therefore, whatever amount of heat, whatever amount of work is given to this container is converted into work. So losses is zero. So we can write from the formula of thermodynamics P is equal to W. P is proportional to W. So that's why we write over here W is equal to Q. So I compare this equation and write over here the value of Q is equal to W, which value is 6283185. Mass is given 1 kg. CV is given and its value is 800. And delta T I write over here as it is because we need to find the final temperature. Okay, so that's why I put over here the value of delta T as it is. So from this relation we can find the value of delta T, and delta T is equal to 785.39. Okay, this is the delta T, but we need to find over here the final temperature. Okay. In this equation also the value of temperature is given, and the value of temperature is here the value of temperature is not given, but we can find with the help of equation, because here T is given, pressure is given, V is given, mass is given. Okay, so we can find with the help of P is equal to MRT. Okay. R is also given. Value of R, Cp minus Cv is R. We will know R is equal to Cp minus Cv. So it is 200 per kg into. So from that equation we can find the initial condition PV, P1, V1 is equal to AM, R, P1. So from that equation we can find the value of T1 is equal to P1, V1 upon M. So P1 value is already given. This one, V1 is given. Okay. Here we need to find the final step T2. So T1 T1 we need to find. So P1 is given. So P1 is equal to this equation will become P1 into V1 upon M into R. So P1 is equal to 105. V1 is equal to 1 meter cube. M is equal to also 1 meter cube. R is 200. So if we divide this value, we get the final value of T1, and T1 is equal to 347.22 Kelvin. So this is the value of T1. Now here you need to find the T2. So delta T, we know delta T is equal to temperature difference, and it's equal to T2 minus T1. So from this equation, T2 is equal to delta T plus T1. So delta T value is 785.39 plus T1 is equal to 347.22. So take the summation of this and you can find the value of T2, and T2 is 1132.52 Kelvin. So this is the value of T2. Final temperature of this gas when you apply some work. So initial condition, pressure and volume is given in this data. Okay. And from the V equals to MRT equation, you find the temperature over here. And then after using this equation to find the value of delta T, and from the delta T you can find the final temperature of this fluid which are inside this rigid container. Okay. So it's easy to understand. Now next example, the example number 11. The example number 11 is from the GATE 2015 step 2. So here the 1 kg of air from given data I write over here. Given data. So mass is 1 kg. mass is mass, sorry for disturbance, mass is equal to 1 kg. Okay, R is given and its value is 287 joule per kg into Kelvin. It is a reversible process. Okay, between the equilibrium state, two equilibrium states are given. One having the temperature with the 20 degree, 20 plus 273, it is 293 Kelvin. 293 Kelvin. And the volume is given, and volume is 0.9 meter cube. Second state is given, and second state is T2. And T2 is also the same temperature, 20 degrees C. Okay, and the volume that is given 0.6 meter cube. And here you need to find the H2 minus H1 change in entropy delta H. Okay, so here from this given data you can observe this thing, the both temperature is same. T1 and T2 both are same. T1 is equal to T2. Just become isothermal process. So remember the previous slide. If you know the isothermal process, then if you know the TDS relation, or you can refer the previous slide in which we already discussed the TDS relation, where we derived an equation delta S is equal to CV ln T2 by T1 plus R ln this T2 by V1. This relation we already derived. Okay, from the TDS relation this equation is come, but here the temperature is same T1 and T2. So if you take the logarithm, then this value becomes 0. Final equation is this. So put the value whatever the data is given in this example. R is given 287. Okay, ln mass is 1 kg. V2 is given and V2 is 0.6. And V1 is given and this 0.9. And if you calculate this value, then you get the answer minus 116.35 joule per kg. This is the value for delta S. Okay, so you can now understand what is the importance for the theory part. If you know all the relations, then you can easily find the value of the example. Yes, theory part is very important for us. Now, the next example number 12, and it is somewhat tricky. So let's start with this example, and it is from 2014, yet site number 3. Okay, so it is somewhat tricky. So let's start with this. So from this example, here ideal gas initially at pressure P1 and temperature T1. So both values P1 and T1. At first, it is undergoes at constant pressure 1 to 2. Okay, so that P2 is equal to P1 by 4. Okay, this relation is given between P1 and T2, and it is undergoes as constant volume. Okay, and the constant volume, their relation is given between P and T1. So you need to find the ratio of final volume to initial volume. So from the given data, you can find in the relation P2 to P1 by 4. This relation is given, and second one relation is equal to P3 is equal to T1 by 2. And here you need to find is the ratio between the final volume V2 and initial volume V1. Okay, so it is very simple. So let's start with this. I draw over here the PV diagram. So you can easily understand. The first process is 1 to 2. In 1 to 2, there is a process with a constant pressure process. The constant pressure process we know we can write by the straight line. This is my state 1, my state 2. If I write over here the pressure is P1 volume is V1 and temperature is T1. Okay, here at the state number 2, I write pressure is P2, volume is V2, and temperature is T2. But the relation is given over here, P2 and T1. P2 is equal to T1 by 4. T1 by 4. Next process is carried out, and it is undergoes as constant volume. So I need to draw the same vertical line, straight vertical line. This is the state 3, 1, 2, and 3, and here the pressure is P3, volume is V3, and temperature is T3. But the relation is given between T3 and T1, and this T3 is equal to T1 by 4. So these things is given in this example. Now you need to find the ratio between the volume, initial and final volume. The initial volume is V1 and final volume is V2. So you need to find the ratio between the V3 by V1, not V2 by V1. Here it is V3 by V1. Okay, so let's start how we can calculate. So from the process 1 to 2, if you see the process 1 to 2, it is P1, V1 upon T1 is equal to P2, V2 upon P2. Okay, but here the pressure is constant, so P1, V2 are same, so we are cancel out over here. So from this relation, the V2 is equal to P2 by T1 into V1. Okay, so this is the relation V2 and V1. Okay, so here if you not go too deep and to write the process 1 to 2, so we will just start with the process 2 to 3 and process 2 to 3, and process 2 to 3 is over here P2 V2 upon T2 is equal to P3 V3 upon T2. But here the constant volume process, so V1 and V2 is cancel out. Okay, so you can write from this process also P2 by P3 is equal to P2 by P3. So from the given relation, we have to find the value of P2, put over here, and then combine this. But I can not go with this process and directly find the answer from this equation, because here you need to find the V3 by V1. So I write this equation V2 by V1. I put over here into millimeters. So V2 by V1 is equal to T2 by T1. But here we know, here the process 2 to 3 is a constant volume process. So here V2, here it is V2 is equal to V3. So I can write over here V2 is equal to V3 and V1 is equal to, but the temperature T2 value is given 3T1 by 4 in the data. This values are given in T1 as it is. Okay, T1 cancel out, so your value is given 3 by 4. Or you can write over here V3 by V1 is equal to 0.75. So here you can directly find the value of pressure, volume relation by using this equation, or you can go with this. Okay, you need to find the P2 over here, put this value over here, and then the process becomes very long. But here it is a easy method. We can go with this and find the value. So its value V3 by V2 is 0.75. Okay. Now the next example, and this is the example from 2013 get. Okay. So here the given data. In given data we have a cylinder. Okay, cylinder diameter with an ideal pressure is given. Okay, 1 bar. The gas is compressed, reversible isothermal process. The isothermal process is given. So it is important for us to choose the equation isothermal process. Okay, and the pressure is increased by 5 bar. We have to find bar. So when, for example, volume is given 5 meter cube, pressure P1 is given 1 bar, And final after compression, the value of pressure P2 is become 5 bar. Okay, and here you need to find work done. Okay, so this data is given. Okay, and we know the equation for work done for isothermal process. We already derived these things in the previous slide. That how we can find the value of work done. So work W is equal to P1 V1 Ln. This is P1 by P2. This equation already we derived in our previous slide for isothermal process. How we will come? We can know from the previous slide. The previous P1 is 1 bar value, but here we have converted into Newton per meter. So 1 into 10 raised to 5. V1 is given, or here the value is given, initial volume, and it is 5 meter cube. Length, here V1 is equal to 1 bar, P2 is equal to 5 bar. So put the value and find the answer. You get the value of V1 is equal to minus 804.7 kilojoule. Okay, but here the negative sign means that here it is a compressive work because compression is carried out. Compressive work. That's why it is negative sign. Okay, so if you want to remove this, I need to find this is the compressive work. And this is 0.7 kilojoule. So this is the value for work done for the compression. So let's start with the next example. And here it is the example from 2012. Whatever the data is given, for it. Ideal gas is given, mass m kg, temperature is T1, undergo reversible isothermal process. So now we can observe how many examples are asked from the isothermal process. The isothermal process initial condition is given, final condition of pressure is Q2. Losing the heat during the process is Q, and we need to find the entropy change. So entropy change here we have to find. So we know the value of or we know from the TDS relation that TDS, one relation we established in the TDS relation explanation, TDS is equal to dU plus TdV. Okay, this is the equation number 1 in the TDS relation. The second equation we already derived that TDS is equal to dH minus VD. If you remember this thing, and you can understand this thing. But here the isothermal process. So for isothermal process, the internal energy change will become 0. So dU becomes 0. dU becomes 0. So this value becomes 0. So your equation will become TDS is equal to PdV. But here you need to find the entropy change. So right over this equation ds is equal to P upon T into dV. Okay. But the problem with this is here the P and T both are constant because the integration is carried out with this V. So I try to rewrite this equation. I have a PV equals to MRT relation. Okay. So if I rewrite it, then it's the P upon T is equal to MR upon V. So this value P upon T in this equation will get over here MR upon V into dV. Now integrate this value. Integration. So if you integrate this value and ds 1 to 2 MR 1 to 2 1 upon V into dV, then you know this value is S2 minus S1 is equal to M into R. Here it is Ln, it is V1. Okay, so you can establish the relation in that way. Also, then this is the isothermal process. So if we write this equation V1 upon T1 is equal to T2 V2 upon T2, this is the PVT relation, but temperature is constant. So I write over here V1 T1 cancel out. So V2 by V1 equals to V1 by T2. So I can write this same equation in that way. Not then V1 by T2. Okay, so you can write this both equation for entropy change in form of volume and pressure. Okay, substitute from the given relation. So now we are the next example. It is from 2011. We get 2011. It is some 50 example. So whatever the given data, I have a less space. I divide this one part into two parts. Okay. Here the two processes given, two stations given, actually P and Q. Initially we are step 1 or step 2, or we can say P and Q given. The direction of flow, it depends on the pressure and temperature condition given P and Q. One experiment, here it is data from experimental side. The condition at step P is given. So at step P, the pressure is equal to 150 kilopascal and temperature is equal to 350 Kelvin. Okay, and at station Q, the value of temperature is given PQ, and it is 300 Kelvin. CPCV and R value is given. Okay. Here the first we need to find if the air flow from the station P to Q, the maximum possible value of pressure at the station Q is close to. So here you need to find the value of PQ. What is the pressure? First answer is this. And second answer is this over here. If the pressure at the Q is 50 kilopascal, so pressure at the Q is given, it is 50 kilopascal. Then you need to find the value of change in entropy delta S plus Q minus SQ. Okay? So these two answers we have to find. Here we have to read more time this given data. In experimental setup is given flow from P to Q. Direction of the flow depends on the pressure and temperature condition, and the temperature and pressure condition at P is given 150 and 30 kilopascal. Temperature at Q is given. Okay, and air properties of the air is given. If the air is flow from shell to the maximum possible value of pressure, it's we need to find. So PQ we need to find, and if the PQ value is given, we need to find the entropy. So here this is the process. You can see it is a adiabatic process. And for the adiabatic process, we know the equation is relation between pressure and temperature. Pp upon Pq is equal to pressure in P upon at point P upon point Q, gamma minus 1 upon gamma. We already know T1 by T2 is equal to T1 by T2 plus gamma minus 1 upon gamma. This relation is in the form of P and Q. Where I go here. Here you can find the value of gamma, and gamma is equal to Cp by Cv. So Cp is given 1.005 and Cv is given 0.718. So from this value, if you find the value of gamma, and the gamma value is from 1.3. Put over all the values. Cp is given, Tq is given, pressure at P is given, so you can find the value of Pq very simply by putting the value in calculate. So you get the value of PQ from this relation 86.6 kilograms. This is your first answer. Yes? But here for the answer, this is not first answer. But here it is given, if the value of PQ is given 50 kilograms, we need to find delta S. Okay? So here we know for the adiabatic process, delta S. From previous relation, delta S is equal to Cp ln equal to T2 by T1, so it is equal to Tq by Tp minus R ln is Tq by Tp. So put the whole values over here. Cp is given 1.005. ln Tq is given 300 Kelvin. Cp is given 350 Kelvin, minus R is given, R is 0.287, ln Pq is given 50 kilopascal, Pp is given 150 kilopascal. Okay, so the value, and if we calculate the whole equation, then we get the value of delta S is 0.160 kilojoule per kg Kelvin. So this is the value for delta S, change in entropy ST minus SP. Okay, so here it is a adiabatic equation. We are using d2 by d1 is equals to d2 by d1 to gamma minus 1 upon gamma is equals to d1 by d2 to gamma upon gamma minus 1. So the same relation we are using here. Now next example number 16, and it is from GATE 2010. So let's start with this example number 16. So example number 16 is all about the nano atomic ideal gas, right? Nano atomic ideal gas, adiabatic index given. Adiabatic index is gamma is value 1.67, molecular weight m is given and it is 40. Adiabatic compression is given and it is P1 is equal to 2.1 megapascal. And temperature P1 is equal to 300 Kelvin. P2 temperature is given over 0.2 megapascal. Okay, and universal gas constant, I think RG is given, it is 8.314 kilojoule per kg into Kelvin. Here you need to find Kelvin. Okay, this is the adiabatic process. So for the adiabatic process, we know the equations are work done, and it is P1 V1 minus V2 upon gamma minus 1. This is the relation which we are using for the find out the value for work done. But here the P1 volume is not given, so we need to convert this because temperature is given. Okay, P1 is given, and so that's why we need to calculate this value. An adiabatic process is given. We need to convert this equation in form of temperature. So P is equal to MRT, so you can write over it MRT1. M is 1 kg, so I do not write over here. So RT1 minus RT2 upon gamma minus 1. So your equation will become RT1 minus T2. So now your equation, say example will become simple. T1 is given, but T2 is not given. So from the adiabatic process, because it is given process is adiabatic, so we can write already discussed in the previous example. That's why G2 by D1 is equal to G2 by B1 plus to gamma minus 1 upon gamma. That's simple relation. So gamma is already given, so put the values to find out the T2. So from the given relation, if you find the value of T2, then it is 396.18 Kelvin. Okay, and here also we require one more thing, is R. So we know that universal gas constant RU is equal to gas constant into M. M is a molar weight or molecular mass. So here you can find R is equal to RU by M. Here RU is given, and it is 314, M is given, and M is 40. So if you put the value and find out the R, then its value is 0.2075. 00 per kg into this is R. Put this value over here and find out the W. So R is 0.20785. P1 is given 300 Kelvin. P2 is given 396.18. Gamma is given 1.67 minus 1. And if you put the value and calculate the answer, we get the value of work over here. It is minus 29.7 kilojoule per kg. This is your final answer. Here the same way, answer is minus. The reason behind that it is a compressive adiabatic process. That's why it is compressive work. We have to do minus 7. So you can calculate it that way. Now, the next example from the 2009. Okay. And here the value is 2009 718. So it is not right over here, but I think 2009 7.
So already there is one second. This from 2009 set. So in frictionless piston cylinder device is containing the gas initially 0.8 megapascal and 0.0135 meter cube. Set on always practically at constant temperature. So temperature is constant for isothermal process. And the final volume is 0.03 meter cube. You need to find the work. So let's write some given data. So pressure P1 is given and it is 0.8 megapascal. Okay, and volume V1 is given and it is 0.015 meter cube. Volume V2 is given and it is 0.030 meter cube. Here we have to find the value of work during this process. Okay, here volume is increased or decreased. Volume is increased, so this is the expansion process. You can give this any value. So it is whatever the value you give over your work, it is positive. And the temperature is remains constant with the isothermal process. And we already discussed for the isothermal process, work equation is equals to P1 V1 Ln V2 by V1. Okay, so P1 0.8 megapascal, so converted into pascal, so get 10⁻⁶. V1 is given 0.015, length V2 is 0.03, and here it is 0.015. So if you calculate the value, we find the value of watt, W is 8.32 kilojoule. Okay, this is the work. This is the work. Sorry, next value is kilojoule. So from this equation we get the value in joule and divided by 1000. Value is get this value. That's very simple example. So if you see this video from the starting of the example, where we start calculating the example, just you find these things. So most of the examples comes from the TDS relation, one question, and second is for isothermal. And third one topic is from, we can say, piston cylinder, adiabatic process. So if this is the solution of the problem from gate 2000, I think 2018 to 2009. So we 17 questions we already solved. 17 examples. And most of the examples they are asked from this photo. Okay? So this is my analysis. So you can understand the importance of the theory. If you know the theory very well, you can easily complete your exam, or you can easily calculate your question example of the thermodynamics in very time.
Now example number 18 from GET 2019 set 1. So here I will try to take the 2019 example. Okay, here it is, the data is given, mass 1 kg, initial temperature and pressure is given, allowed to expand isothermally, isothermal process is there, and pressure, final pressure is given, assuming the air is an ideal gas, so we have to choose this is the ideal gas, and gas constant is given 2.87, and find to entropy, change in entropy. So same as it is here, I try to write the given data. So given data, in given data we had mass 1 kg, okay, initial temperature T1 and it is 300 Kelvin, and isothermal process, so temperature is same, so T2, the reason is isothermal process. Then pressure is given, P1 is 10 bar, and after expansion the P2 is 1 bar. Okay, and R is given 0.287 kilojoule per kg into Kelvin, and we need to find delta S, change in entropy. So as usual for isothermal process we had a TDS relation. So if we recall the TDS relation, we know the equation of TDS delta S is equals to mCp ln T2 by T1 minus R ln P2 by P1. But here the process is isothermal, so T1 is equals to T2, so this values become 0 because T1 is equals to T2. Isothermal process, isothermal process. Okay, so put the values delta S minus R is given 0.287, ln P2 is given 1 bar and P1 is 10 bar. Put the value, and if you calculate then you get the minus answer. So finally minus minus plus, and your answer is 0.668 kilojoule per kg into Kelvin. So here this is the delta S for given data, change in entropy. Okay, next problem, example number 19, and it is from GATE 2019 set 1. A gas is heated in duct as in flow over a resistance heater. Consider a 101 kilowatt heating system. Gas enter the heating section of the duct at given condition, 100 kilopascal pressure and 27 degree temperature, and volume flow rate is given 15 meter cube per second. If the heat is lost from the gas in the duct due to the surrounding at the rate of 15 kilowatt, the exit temperature of the gas here you need to find, and some properties of the gas is given, Cp is given and R is given. So example is very simple. Here we can say one duct is there in this way. Here the some coil and gas is flowing. This is a coil, and here it is a gas in and out. Okay, this condition. So here this is the inlet. So here pressure is given 100 kilopascal, temperature is 27 degree, and flow rate is given 15 meter cube per second. Okay, and here you need to find the temperature at the final point. So T2 you need to find at the exit. Also here the given the Q amount of heat is rejected, so we can say it is lost. So from given data, here Q is equals to amount of heat which are rejected. So I put over here minus sign because heat rejected, heat lost, and work we are supplied to the system. So we already know the thermodynamics concept, so we need to write over here minus 101 Kelvin because we are supplying the energy to the system. That's why we put minus sign. Okay, and this values at the inlet is given, and here we need to find temperature at the exit. So from the given data we can find the mass flow rate of the air first of all. So we know PV is equals to MRT, so mass flow rate M is equals to P1 V1 upon R into T1. So P1 value is given and it is 100 kilopascal. V1 volume in meter cube per second. So it is flow rate, that's why here in meter cube per second. This value is kg per second. So we need to directly write over here. And R is 0.5. Inlet temperature is given T1. T1 is 27 degree plus 273, so it converted into Kelvin 300. If you calculate from this equation, the value of the mass flow rate is 10 kilogram per second. Okay, so here we can say the mass flow rate of the 10 kilogram per second. This much amount of air is flowing to this system. Okay, duct. Now we need to find the temperature T2. So if we apply the first law of thermodynamics and steady flow energy equation, then we find what is the steady flow energy equation. Here we know it is H1 plus GZ1 plus Q is equals to H2 plus GZ2 plus W. Okay, and remaining terms I do not write over here because we say it is a neglected. Also this term is also neglected because the same reference side. So I write directly over here H1 plus Q is equals to H2 plus W. Okay, so here we can write, and here it is a total value, so multiply with the mass flow rate. Okay, and if I write this term, then we can write over here Q is equals to mass flow rate H2 minus H1 plus W. Okay, here I write over here, this is the mass flow rate, so mass flow rate. So here the mass flow rate is given and its value is 10 kg. H2 is given. Okay, here H2 is not given, but we can write it is Cp T2 minus Cp T1 plus W, because H is equals to Cp delta T, that's why. So Cp is common, so mass flow rate 10 so Cp 10, so 10 mass flow rate, and Cp value is 1 into T2 we have to find minus T1, and T1 is given and it is 300 Kelvin plus W is minus 101, and here it is Q is a minus 51. So from the given detail you can calculate the T2, and the T2 is 32 degrees centigrade from the given value. Okay, so this answer may be come into the Kelvin, you need to convert into degree centigrade, so you can easily get the answer. So this is our answer. So here the important thing is SFW equation and gas characteristic equation. These things we are later on study in the part 2, how SFW equation is work. Here I am taking just a small part of this, that's why I am not go with much more. But when we discuss this thing in part 2, at that time I will show you how the SFW equation is come and how it is applied for the different system. Okay, so it is very easy example. Now the next one, it is example number 20, and it is also from 2019 GATE. It is given data. Here the 1 mole H2 gas, rigid container, capacity is given, so volume is given 1000 liter, So we say 1 meter cube. Temperature is given, it is 27 degrees C. T1, T2 is given 37 degrees C. Okay, change in the pressure of the container gas, okay, we need to find, and here it is also ideal gas. Value of R is given. Okay, so we need to find the change in temperature, sorry, change in pressure. So delta P, I think delta P, P2 minus P1 we need to find. So let's start from here. Volume, initial volume is V1 because it is a rigid container, so volume does not change. So V1 or V2 both are same. Let's start the gas characteristic equation. P1 is V1 is equals to N R T. Here I am taking, because the values does not given into kilogram, here value is given into mole. So this is the molar gas characteristic equation. For here M is not mass but it is the mole, number of moles. Okay, so it is M is replaced with the N in such a cases, nRT1. Okay, put the value. So if you put the value, then find the P1. P1 is equals to N R bar T1 upon V1. Okay, and here the volume N, the 1 mole, N value is given here, 1 mole. So N is equals to 1 mole. So I write over here N is equals to 1. R is also given into mole, so it is 8.314 into temperature. Temperature is given T1. T1 is 27 degree. So if you convert into Kelvin, it is 300, and volume is also given 1. So if you calculate the value, then you find the P1 is equals to 2494.2 Pascal. This is my first value of P1. P1 is equals to 2494.2 Pascal. Okay, the same equation. So if you want to understand this equation well in manner, so you can derive the unit, it's come or not, you can easily get the answer. So if you want to doing this, then it is here N is a mole. Sorry, N in mole, N in mole, sorry, N in a mole, okay, R in joule per mole into Kelvin, T in Kelvin, and V in meter cube. Okay, liter or meter cube. So you can see over this value and this values are cancel out, and joule is a Newton per, joule is nothing but it is a Newton into meter. So here meter is also cancel out. So your whole values become Newton per meter square. It is Pascal. Okay, so that's why we are here directly taking the values in Pascal. Now the second part, here P1 is calculated, we need to find the P2. So second part, it is a rigid container, an ideal gas. So we can use the same equation for PV is equals to MRT because volume are same. Here the volume V1 is equals to V2 is equals to 1 meter cube. So values are, volume is given same. So if you try to write it, then we can find P1 here from here, this equation. From this equation we can write N R T1 upon P1 is equals to N R T2 upon P2. So here it is, both values are same. So we can, because the condition is given here, rigid container. So the volume is same. That's why we are using this relation. So from this relation you can find the P2, and P2 is equals to here T2 by T1 into P1. If you put the values here, the temperature T2 is equals to 37, so its value is 310. P1 we already find 2494.2 divided by T1. T1 is 300, and finally you have a P2 value, and P2 is 2577.34 Pascal. Okay, so we had a T1 and T2 both value. Now we can find the value of delta P, change in pressure, because we need to find this. So its value is P2 minus P1, and final answer for this example is 2577.34 minus 2494.2, and you get 83.14 Pascal. So this is not delta S but delta P, change in pressure, and this is my final answer. Okay, so here the new things is there. The PV is equals to MRT equation in form of mole. PV is equals to nRT, where N in the form of mole, not in form of kg. And here the rigid container is given. That's why we are taking the volume is same, rigid container. And we are applying both the time PV is equals to nRT relation and find the value of delta P. Okay, so next we had a 21 number, and it is the last one for today's session, part 1. So here it is a 2019 set 2 example. So given data, water flowing 1 kilogram per second. So mass flow rate of water is given. If I write over here, mass flow rate of water is 1 kilogram per second. The system is heated using the electric heater such that the enthalpy of the water is increased by 2.5. So enthalpy increase, so H2 minus H1 value is given, increase 2.5 kilojoule per second, kilojoule per kg, and the specific entropy is increased by 0.07. So S2 minus S1, change in entropy is given 0.007 kilojoule per kg into Kelvin. The power input to the electric heater, so work input is given, and its value is 2.5 kilowatt. And there is no other work heat interaction between the system and surrounding in the previous example number 20 I think, in which there is a loss, but here there is a no loss, so we are not considering Q over here. Q is 0. Okay, assuming the ambient temperature, so temperature is given 300 Kelvin, and you need to find the irreversibilities rate. Okay, so this is a new term actually for us. We never discussed this term in our lecture. So here I directly write the values. Later on we discuss this irreversibility. So irreversibility can be defined as irreversibility of the system. It is measured with the I, and its value is mass into T0 into delta S, change in entropy. Okay, this is the measurement of irreversibility. Mass flow rate is 1 kilogram per second. Temperature is given 300 Kelvin, and change in entropy is given 0.007. And finally, by calculate this, get the answer 2.1 kilowatt. Okay, so this is the term which called irreversibility, and we can find with this equation. Irreversibility we can find with this term we never discuss, but we can discuss in the next part too. Okay, so this is the analysis of the 4 gate question which asked from 2009 to 2019, last 10 years question solving, and this topic is all about the, we can say here, all about the thermodynamics relations and all this thing. So thanks for watching this video, and we are coming with the next videos part 2, in which we discuss the different thermodynamic cycles, okay, and based on the example, based on the THA cycle, which are asked from 2019 to 2019, last 10-year question. So thanks for watching and have a good day. Thank you.